I'd like to welcome you all here to another in our WestGrid's seminar series. Today we're going to be talking about HPC in the cloud, and it's going to be presented by Ryan Enge, a member of our WestGrid support team located at the University of Victoria. Ryan.
Welcome everybody. So this is HPC in the cloud, or more specifically HPC and OpenStack. I've been working on research computing here at UVic since 2004, and I've been working on WestGrid systems since we got Hermes and Nestor at the end of 2009. In May of 2010, I helped deploy the first IaaS cloud at UVic, which I believe was also the first cloud within Compute Canada, and is still in production today. So I'm just going to start by saying that the current state of the cloud is that we're in beta testing mode. We have a limited number of users currently that have been given access to the system. So we're still working bugs out, and we're still in heavy development. So there's still a lot of changes that are to be made in the upcoming weeks and months regarding the actual name of the cloud is going to be rebranded. We're going to be updating things like the flavors of the VMs, basically the CPU, memory, disk specifications, the default images that we provide, the quotas for the individual projects, and several other things around the cloud that we have to do with this new rollout of this new functionality. So I would ask you this time if you could please hold off on requesting access to the cloud, and there'll be some kind of a mail out or something to inform people when the cloud is actually going into production. The other thing I'd like to mention at this point is that we're actually doing this in collaboration with the University of Sherbrooke. So we've been working with them since the beginning, getting initial RFPs and stuff for the equipment, all the way down now to working on the different policies that we want to decide to try to create sort of a unified view of the cloud within Compute Canada. So today I'm just going to give a quick overview of what OpenStack is, talk about the OpenStack infrastructure that we have at UVic, give a quick overview of some of the individual OpenStack components, talk a bit about how you can get access to OpenStack via the web interface and command line interface, show some example VMs, Windows and Linux, talk about some benefits to HPC, and some example use cases, and then give a few demos. And if we have time at the end, I'll talk a little bit about getting data in and out of your VMs. So this is something I picked up from Wikipedia. So basically what I want to focus on here is that we are providing an infrastructure as a service cloud. So there's basically three different types of clouds that are available to people. So those would be SaaS, PaaS, and IaaS. So SaaS, or software as a service, would be something like Gmail or Google Apps, and PaaS, or platform as a service, would be something like a web service provider that gives you sort of a LAMP, Linux, Apache, MySQL stack, where you can develop a web application and you're not worried about the underlying physical hardware. And finally, what we're providing, which is IaaS, or infrastructure as a service, it provides the processing, the networking, and the storage, and the user provides the operating system and the software and services that are installed on top of that. So we just sort of provide the basic infrastructure, and everything else is left up to the user. So there's also several different ways to access the cloud. We can access it via the web interface known as Horizon, through the command line interface, or through the RESTful API. I'll be demonstrating the access via the web interface and the command line interface today. So just a bit about the infrastructure here at UVic. So what we've deployed is the front-end servers, or we call them the control nodes. There's three of them in a high availability active-active load balance configuration. So this allows us to hopefully scale really well as we increase the number of compute nodes in behind the cloud control nodes, and also the users that will be accessing the cloud. We decided to separate Neutron, which is the networking portion of OpenStack, onto a separate set of nodes, and they're currently running at an active-passive pair. I'll just mention at this point that the configuration we have now could very well change based on our experience that we have with the cloud and how we see things moving forward. Also, we have 40 compute nodes that are for running the virtual machine instances. And now the backend storage that we're using for OpenStack. OpenStack is extremely flexible. There's many different ways to configure it. And so we've chosen to use Ceph. You can get some more details at ceph.com about what Ceph is. It's basically a distributed object and block store and also a file system, and it scales extremely well. So for Ceph, we have our 3 monitoring nodes, which are sort of manage where the blocks are actually stored within the OSD servers. Those OSD servers, which we have 13 of, have 12 4-terabyte hard drives, which gives us a total of somewhere around 600 terabytes of raw storage. With Ceph, it has the idea of replicas, so every block is actually replicated n times, and you can pick what you want that to be. So obviously, the more you're going to replicate, the more expensive your storage is going to be. So we've picked 3 as sort of a good sort of disaster recovery / cost benefit. I'd also like to mention at this time, we have no automated backups of Ceph. The only way that Ceph provides a backup at its current state is actually to back it up to another Ceph cluster, and we don't have another 600 terabytes of data that we can actually push this into. So our plan for the short term is to give users that have, say, persistent VMs running in the cloud the TSM client, and then they could do their backup to our TSM here at UVic or maybe to the one at Silo. Okay, so the physical compute nodes are sort of split into 3 different components. So we decided that for HPC style jobs, we didn't want to do an over-provisioning of CPU. So in a general cloud, if you're going to access something like Amazon, you're going to have some large over-provisioning of CPU resources. So for example, on our persistent nodes, we're doing a 10-to-1. So that's 10 virtual CPUs mapped to 1 physical CPU. So in our scenario, we have 2 physical machines that we've allocated as persistent nodes. That's a total of 32 cores. With hyperthreading enabled, that's 64 cores, and then you times it by 10, so we get essentially 640 virtual cores that we can allocate to images for persistent type purposes. Each node, there's also sort of 2 main node types. We have our 256 gigabytes of memory per node, and we have 512 gigabytes of memory per node. All the nodes are interconnected with 10 gigabit Ethernet. And so the persistent volumes will actually be served directly out of the Ceph file system. So Ceph provides the block storage. For ephemeral nodes, so ephemeral is something where you boot it up, you do something on it for a while, maybe you run a compute job, you shut it down, and then it's gone forever. So this is something that's not persistent, it's not going to be around for very long. And so we keep that data actually locally on the compute nodes themselves, where we have about 1.6 terabytes of storage. And we felt that this was a good trade-off between sort of overloading the central storage and scaling out with the compute nodes. So for the small memory, relatively speaking, nodes, we have 30 of those with 480 cores, and then once you enable the hyperthreading, that puts it up to 960 virtual CPUs. And then again, we have the big memory nodes. Currently, we have 8 of those nodes, so we have 256 virtual CPUs available for user jobs. So basically, what we'll probably do is, at any given time, we'll just be running whatever jobs on whatever nodes. If some user comes in with a large memory requirement, then what we can do is actually live migrate the VMs onto another machine to free up the memory on these big memory machines for large memory type jobs. So that's just one sort of great feature about OpenStack, is the ability to actually move around people's instances, so we can do things like patch the underlying operating system of the hypervisor, or do maybe do some maintenance on the hardware or firmware updates, etc. This is just a subset of the OpenStack components that I thought would be sort of the most interesting. OpenStack is constantly sort of separating new functionality into new projects so that they can focus on, sort of on that core feature set that they want to provide. So Nova is sort of the back-end compute infrastructure. Keystone is the identity, so the authorization and authentication service. Horizon is the dashboard that you'll be interacting with when you're using the web interface. Glance is the client that you'll be using, and it manages all the images within OpenStack. Cinder is the block storage, so that would be sort of a persistent VM would be running from a block storage served up via Cinder, which in the back end is Ceph. Neutron is the networking that we've decided to use. There is the legacy, which is an example of how the project gets split up. There is a Nova networking component that is still can be used today. It has a lot less features than what the new Neutron networking service provides, so we've decided to go ahead and use Neutron. And I'll just talk a bit about Neutron. Neutron has several different underlying backends that it can leverage. So it can use VLANs, flat network, GRE tunnels, and VXLAN. So VXLAN is this, it's a software-defined network, and it basically does some UDP. It encapsulates all the traffic within UDP packets. And what this gives us, what software-defined networking gives us the ability to do is for users to create networks within their projects, within OpenStack, without worrying about what IP space. They're not going to clobber anybody else's IP space. There's actually no need for a sysadmin or a network admin to intervene when you're creating a network. You can do it with all by, like, without any intervention from a sysadmin, so it makes it very flexible and takes the load off of us. So the last thing I kind of wanted to mention is sort of a neat project, which is sort of in its early stages, which is the Ironic. So this is actual bare metal provisioning of compute nodes. So this would essentially take out the virtualization layer from OpenStack and give you bare metal performance of your compute job. So this is something that we're interested in looking at a future date. So essentially we get the nice, front-end functionality of OpenStack, and then we'll get the nice back-end performance of running on physical hardware with no virtualization overhead. So this image is a bit hard to read. I just wanted to kind of give an overview of the components. So the two outermost components are what we would consider the control nodes. In our installation, we actually have 3 of those. And then the middle one is the compute node. So this just sort of shows that there's lots of different pieces within OpenStack, and there's a lot of different communication types. So I just wanted to kind of highlight the different kind of communication types, starting from the legend at the bottom, from the top down, which is SQL, REST API, load balanced REST API, AMQP, HTTP dashboard, and load balanced HTTP. So there's a lot of different moving parts within OpenStack, and so far we've had a few issues, sort of getting used to the way everything works and keeping things up and stable. But as we progress further, I think this will be an excellent platform. And I borrowed this image from Mirantis, which is where I did some OpenStack training earlier in the year. So now, the fun part. So to access our OpenStack cloud currently, we have nefos.westgrid.ca. So this is part of the policy changes that we're implementing, and soon this will be known as west.cloud.computecanada.ca, and Sherbrooke's site will be known as east.cloud.computecanada.ca. So the other way to access OpenStack that I'm going to show today is via the command line. There are actually 2 different styles of Python clients. There's the original clients, which were broken up into each of the individual components, such as Nova, Neutron, etc. Or there's the new OpenStack client, which basically encapsulates all the functionality into one Python client. And so that's what I'm going to focus on today. Okay. So this is what the web interface looks like when you first log in. So up at the top menu here, this is the list of projects which I have access to. Most users will probably have 1 to 2 projects in here, so aren't really concerned about this. But this is something to keep in mind when you're accessing it via the command line. You have to tell it what project you're part of. So this overview summary basically lets me know several things about my project. It tells me all the different quotas that I have and also where all the usage that I'm currently using in the cloud. So we can see I'm using 305 instances. So instance is just a virtual machine. And then I have several different flavors of my instances, so that's the different CPU types. So I'm using 7 out of 20 of my virtual CPUs. So these are the quotas that will probably be changed between now and when we actually officially roll this out in production. We're trying to figure out a sort of a general quantity that people are going to use that gives them sort of a way to test without consuming a bunch of resources and then leaving their VM sitting there running idle. You know, and then never coming back. So this is where I can actually boot up a VM. So as you can see right now, I have 3 VMs that have been booted previously. So this information gives me things like the image that they're running, the public and private IP address, depending on if I've assigned a floating IP, the amount of memory and CPU and disk that I've assigned to the machine, the SSH key that I've assigned so that I can log in. And so what I'm going to do now is just sort of walk through a quick VM, booting up a VM. So we'll call this the Horizon. So right now we only have one availability zone, so don't worry about that. So these are the current flavors that we have available. We're going to be greatly expanding this list to make it more flexible for users so that we don't end up getting a whole bunch of requests for, project-specific flavors. We want to try to cover the largest variety of use cases as possible, and so that we sort of create one set of flavors and stick with it. So for now, I'm just going to boot a small flavor. Over here on the right-hand side, you can see what that is going to give me: 2 gigs of memory, 20 gigs of disk space, and 1 virtual CPU. So I can also boot multiple instances at one time from this interface, and what it'll do is actually append the UUID of the image onto that name that you've given it. So we also have several options for boot source. So I want to boot basically an ephemeral sort of HPC style job, so I'm going to be booting that from image. An alternative would be that if I took an image and did a bunch of modifications to it, I could actually take a snapshot of that so that I can then boot that image from now on with my modifications already applied, so I don't have to do that each and every time. So booting from volume would be booting a persistent, say like a web server or something like that. Booting from image creates a new volume, would actually boot an image like CentOS 6.5, let's say, and then convert that into a volume, so then you can then customize your persistent image. So that's the way you would start creating a volume in general. So for today, I'm just going to boot from image. I'm going to select CentOS 6.5. So there's a few other tabs at the top here. So depending on if you have more than one of something, you'll have to make a selection. So if you only have one SSH key within OpenStack, then it'll already be selected. But since I have more than one, then I have to select one. The same is with networking. So I've defined 2 networks within my project, so I actually have to specify which network I want to use. I'm not going to worry about the post-creation and advanced options at this point. So there we go. Now we're launching a VM. So now the VM will go into spawning state, and pretty soon it should go into running state. And I'm just going to show the console view here. So now we can see our VM booting up. And I'll mention this while this screen is up right here, the cloud and net. Excuse me. So when you provision a VM, you want to contextualize your VM. So you want to create a default user account. You want to be able to somehow gain access to this VM that's sort of been generally available to everybody that is part of your OpenStack cloud. So what they use is called cloud init. what Cloud Init does is it has a configuration file, and so for CentOS 6.5, that configuration file currently creates a user named cloud-user, and if you specify an SSH key, it will inject that SSH key into the cloud user's SSH known host or authorized keys file. So this allows you to log into the VM without using a password. And now, in general, none of the VMs that we're providing have passwords for any of the accounts. So you can't log into any of the VMs unless you have an SSH key that's been injected into the image. So the log option is basically just a text version of the console output. On the physical hypervisor, it literally is just a text file that you can cat out or look at. The overview tab is going to give you information about the VM, when it was created, how long it's been up, the flavor that you chose, the IP addresses that it has. So right now I only have one private IP. I could actually have multiple private IPs, multiple NICs, I could have public IP address here. And it also shows you the security groups that have been, which are analogous to ACLs or IP tables rules for this particular VM. And then the metadata associated with it, so my SSH key and the image that I've booted, and also eventually if I attach a volume to it. So that's sort of my next step here, is clicking on the Volumes tab. So what I've done here is I've created an example volume that's only 10 gigs in size. And what we can do is we can attach it to our VM that we just created. So now I'm going to associate a floating IP to my VM. And now I'm logged into the VM that I just booted up using the cloud user account. And as we can see, a new device has been added. So now I can go ahead and mount this device. And I can have a look at my persistent data that I have there. Now I'm just going to go ahead and unmount this device. Okay, where's my web browser? Okay, and I'm just going to shut off this VM. So I can actually shut down the VM, which means it'll stay in this pane and I can boot it up later and it'll keep the same IP address. Or since I don't need it anymore, I could just terminate it and then basically it's gone forever. So the next tab menu item is the images. So this is the images right now is showing me images that I've added into my project. So I've got two images here. One is a snapshot based on another image so that I've made some modifications to, and then one is Fedora 20 image that I uploaded. One thing you'll notice is there's these two columns here, public and protected. So if I make an image public, anybody can have access to it and boot that image. And if I make an image protected, that means nobody can delete it unless they unprotect it. So it's just sort of a safety feature. There's also an option up here for your public VM. So these are all the public images that I have access to as well within OpenStack. So we have our CentOS 6.5 base, a Windows server, and a few others. These are also going to be changing soon. And when it comes to the contextualization piece, I'm thinking that we'll probably standardize on a name like CC Cloud or something instead of Cloud User, or like with Ubuntu, it uses an Ubuntu user, and with Fedora, it uses a Fedora user. So we'll configure all of those images to have sort of the same username, which we'll document in our quick start guide. So next is the security groups. So these are analogous to ACL or IP tables rules, and they're actually dynamic. So if I change one of these rules, it'll affect all the VMs within my tenant that are using this security group. instantaneously, essentially. So I can add access to, you know, if I fire up a web server, I can now open up, let's say, port 80 or 443 and allow web traffic. So what I'll do is just create a new security group, because we may not want to allow web traffic to every single one of the VMs in our project. We may only want a subset that are actually our web servers. So we can create a new security group called web servers. And then we can go ahead and say create a rule. So what we can say is we want to allow HTTPS from anywhere in the world. Now when we go ahead and boot up our VM, we'll associate the web server's security group with it, and then it'll allow port 443 access to all the instances that are using this security group. So the next piece is the network topology diagram. So this gives you kind of a nice visual view of your networking within your project. So I've defined two networks which are independent of each other, even though they kind of look like they overlap. And what this is showing me is we have our public VLAN out here. And for this particular network, we have a router. I can see its IP address, the internal and external IP address. And then I can see the VMs that I have connected to this network. So all these VMs will be using this network, this gateway, to get up to the outside world, unless they have a floating IP address, and then they will use that instead. One thing I'll mention about floating IP addresses is that the VM actually never sees the floating IP. I'll show you later in the example of our Linux VM that it'll only ever see its private IP address. The actual public IP address will be sitting on a neutron node, and it'll be forwarded through an IP tables rule. So most users won't really worry about the networking section. When we create a tenant, we'll be provisioning the network for the user. But this is just sort of a quick overview. So it's the networks I have defined, the subnets I have defined, and you can create subnets that overlap other networks outside of your tenant without any issue, because it's all encapsulated within the VXLAN packets. So when you actually click on your network, you'll be able to see a lot of information. So you can see that every network requires a DHCP server. So when the VM boots up, it gets an IP address from your DHCP server. In our case, we have two, because we have an active, passive, high availability network setup. So there's one associated to each one of the physical network boxes. So Compute Nova would be just a virtual machine, and the router will be the providing the NAT for the compute nodes within the cluster, network address translation. So the final step for the networking is to define a router. As a non-administrative user, you won't actually be able to see the fixed public IP address that your router gets. But since I'm admin, I get to see everything. So basically, you see the internal and external IP address that this router gets. And that's what the VMs will use to talk to the outside world. Okay, so now on to the command line interface. So what I've decided to do here is to actually just do a quick bash script. So this sort of shows the power of the OpenStack command line, and I've asked it to stop at each step so that we can sort of go over things quickly. So the first thing I have to do is set up my environment. So these are some environment variables that you can actually get exported from the web interface. In the Access and Security tab, there's a API tab that you can actually download this text file, and then you can source it to get access to the command line interface. So the first command I'm running is OpenStack server list. So this is going to give me a listing of the current VMs that I'm running within my tenant. So you can see the UUID associated with the instance, and you can also see the networks associated with the instance. And on top of that, you can see the floating IPs that they've been assigned as well. So the flavor list just shows the current set of flavors that we have. So what I'm kind of stepping through here is the process that you'd have to do to actually boot a VM from the command line. You need a certain amount of information to be able to boot a VM from the command line. So these are all the images I have available to me. So unlike the web interface, which separated the private and public VMs, these are all put together into one output, so I can see all the instances that I have access to. So I believe this is because I'm admin, I can see everybody's network. So basically there's been several networks defined so far. And when I boot up a VM, I want to make sure that I'm using the network that I have access to. So now I'm booting a VM. So I've defined the flavor, the image that I want to boot, which happened to be CentOS 6.5. I've told it to use my key from my MacBook and the network and my network that I've chosen. I've given it the name Enge CLI boot. And I've told it to wait. So what it's doing when you wait is it actually waits until the VM has started up. So then I get a little bit more information about where my compute node is physically, or where my virtual machine is physically running, and I get the UUID of the virtual machine as well as a bunch of other information. So now this is showing the console output. So that's basically the text console that we saw through the web interface. So that way you can sort of see the progress of the virtual machine as it boots. So now that we have a VM booting up, we want to be able to log into it. So we can see that I have a floating IP available to me here. That's currently not allocated to anything. So I'm going to go ahead and allocate that to the VM that I just booted. So now if it's booted up already, I can go ahead and log into it. So there we go. Now I'm booted. Now I'm logged into my instance that I booted entirely from the command line. And just to show, the VM only sees its private IP address. It doesn't know anything about that public IP address. So now I can go ahead and shut down this instance. I no longer need it. And we can see now it's been shut down. Okay, so to avoid the wait time, I pre-booted a Windows VM. So I'll just show it here through the web interface first. So unfortunately, I don't think I can actually push Control-Alt-Delete through this client, but I will use the RDP client, which is the preferred method for accessing Windows VMs in the cloud. strange. All right, I might have to get back to that one. So this could be part of the issues that we're encountering occasionally with OpenStack with our deployment. We've had some occasional network blips, and so this could be part of that, or just be something to do with my access configuration or something. Oh, there you go. So here we are in the Windows VM. I just installed Firefox, so from here you could install your ArcGIS software, whatever kind of HPC software that's required that you want to run in the cloud. So basically, the benefits I see for HPC users is that this is an incredibly flexible product. You have the ability to boot Windows VMs, you have the ability to boot Linux VMs, you can do different distributions, you can boot an old distribution that's no longer supported, but you need it for some legacy piece of software. You're no longer bound to the operating system that is installed on the traditional HPC cluster, and say you have a piece of software that you're running that is no longer supported on, let's say, Scientific Linux or Red Hat 7, the local cluster is going to upgrade, and so to finish your computation, you could fire up a few, Red Hat 6 VMs in the cloud and finish off your computation. Another benefit is the large amount of memory that's available on each one of the nodes. So this will allow us to sort of fit jobs that sort of fit in between something that you might run on Hungabee and something that you run on another cluster that may only have 3 or 4 gigabytes per core. With the large memory, you could also do something like a RAM disk for something that's sort of an IO-intensive task, and you could actually have your data sitting in memory to do your processing. Another benefit would be the software-defined networking. So this gives you sort of segmentation from everybody else within OpenStack. So it's an excellent test bed for maybe deploying some new software or doing some other kind of testing before maybe migrating it to a traditional HPC cluster. So this is just sort of to show the extreme of what we can do. We can actually create a virtual cluster. So let's say we set up a VM with a head node and a public IP address. We install Torque and Moab. We create a bunch of compute nodes. And then we have the users issue Q subs from the interactive nodes onto their virtual machines running in the cloud. Another thing we can do with that would be to actually burst our traditional HPC jobs onto the cloud. So we can do something similar where we install the Torque client on a VM instance and get it configured to use our GPFS file system, and a user could, just using the standard Q sub on Hermes and Nestor, could wind up running on a virtual machine on the cloud and not even know it. So this would give us larger memory capabilities for something like Hermes, which only has 2 and 3 gigabytes per core. So I just wanted to mention Cloud Scheduler. It was developed in partnership with UVic and 2 groups from NRC, and it provides the sort of batch processing for the cloud. So a user can actually submit thousands of jobs into Cloud Scheduler, and what it will do is it'll manage the booting of the VMs, and when a VM is available, it will give it a job, and when that job finishes, it'll run another job. So it allows the user to submit thousands of jobs at a single time, instead of firing up the VM and then manually running a job as they free up, or as they finish. And so then the carry on to that is the ability to actually do cloud bursting, so to run at multiple cloud sites. So if you have peak demand, you have a talk or something and you have to get a bunch of data, you could actually burst onto other clouds such as the Sherwood cloud, or even a public cloud like Amazon, AWS, or something like that. So some example use cases. So already I showed the Windows, which some people are requiring for specific pieces of software that will only run on Windows. So that is an excellent win right there. The ability to do some interactive work on the VM itself without affecting, say, maybe doing some work that you would normally do on a head node, but maybe it would be intrusive to other users. We could also run persistent services like a Drupal website that could host the content of your research that you've gathered during the computation on the WestGrid systems. We could also do multiple VMs, like I mentioned before, the virtual cluster. We can actually run MPI jobs, and we can run Hadoop. So we've got an example here where we took 4 VMs, and using SSHFS and no software installed on the VMs themselves, we're using the configured software from Hermes and Nestor to run Hadoop MapReduce. So, I mean, the sky is the limit as far as this goes, no pun intended. And I'm sure researchers will find creative uses for the cloud that we haven't even thought of yet. So I'll give a few quick demos here. So it's a bit small, but I kind of want to fit all these onto one screen. Let's see if we can. So this is sort of an example of a possible interactive job that you might want to run where there's some visual output. So this is the one-dimensional game of life that Belay has set up for me. So you can see the output from the MPI job, and it actually went ahead and ran on all the VMs here. So this is VM 1, 2, 3, and 4. So the next example is just going to calculate pi. This is a good example. It takes a little bit longer to run, so we can actually see the CPU utilization on the node spike. Hopefully that comes through with the web streaming. And there we have the value of pi. This can be tweaked slightly so that we can do more iterations and get more accurate results. So next is Hadoop. So essentially what we have here is using SSHFS, we've mounted the global software and a home file system. So, and we've configured the modules similar to how they're configured on Hermes and Nestor. So I simply do a module load Hadoop. We've pre-populated it with some data, which I'll show here. So we have 2 different text files with words, and this is basically an example to count how many words and how many occurrences of each word within a file. And it's going to distribute it between the 4 different VMs. So we should see here in a minute the CPU utilization on these VMs go up. So I'll just let that run and I'll continue on. So finally, I just wanted to show a few examples of getting data in and out of your VMs. So there's a few services that WestGrid provides that are very useful for this functionality. We can use the own cloud, and that basically gives us 50 gigabytes of storage that we can access from anywhere. We can use Globus Online, which is the more recent setup. And that allows us to transfer data between 2 endpoints. So we can transfer data from, let's say, Silo, or I have data sitting at Hermes and Nestor, or whatever, and I can actually make my VM a Globus Online endpoint. As I showed before, we can do SSHFS and mount, say, your home directory on a cluster, and you can get access to your data that way. SCP and rsync, of course. So I'll quickly log into my VM. So here's my VM that I have mounted using DavFS, WebDav. So I've mounted my own cloud directory here. So I can see the data that's sitting there. I can touch a file. I can then go into the own cloud web interface and see that my file has showed up there. So basically whatever I have in that directory is automatically synced with the own cloud on WestGrid. So the next example is the Globus Online. So basically I'm using an endpoint of Hermes, and I have my OpenStack test VM that I have running here. There's some documentation on how to do this on the WestGrid website that I followed. So basically I can select a file. I just hit go. Hopefully I'm still authenticated. So now we can go back and look at my VM. And there it is, test.pl. Beautiful. So that's pretty much it for my presentation today. I hope it was somewhat useful. And if we have any questions, I can try to answer them now.
All right, do we have any questions at any of the sites?
We have a question from Calgary.
Go ahead. I think we had a question somewhere. I couldn't really hear you.
Are we muted or not?
Yeah. Can you hear us?
Hi, it's Doug in Calgary. Can you hear me?
Hi, Doug. You're pretty quiet, but yeah, we can hear you. Try to speak loudly.
I was wondering about licensing for Windows instances. How is that handled?
So that will be left up to the user. So the Windows image that I booted was actually an evaluation. If you look at the desktop, it actually shows that it's a 180-day evaluation license, and it expires depending on how long you've had it booted for.
But if a user is copying an instance from a list that you provide, I still don't see how the licensing would work.
Yeah, so the Windows VM that we're providing is just sort of to show as an example of the fact that you can boot a Windows VM on the cloud.
Okay, we can explore this more later, I guess. The other thing I was wondering about was monitoring usage and preventing waste. I would think that there would be a lot of potential for users just to leave their VMs running, and so maybe the other aspect of this is the meaning of ephemeral, whether you put a time limit on.
Yeah, so we've had, so this is one of the policy decisions that has to be made. We've had this discussion with Sherbrooke as well, and so we are going to be monitoring and reporting, and we need to be reporting stats back to the CCDB. So we'll be monitoring the VM instances, and we'll probably have some policy that we create around VMs that are just sitting there doing nothing for a certain amount of time before we either shut them down automatically or maybe send a note to the user and say, you're not doing anything, please shut it down.
I think that's one of the beauties of OpenStack is the fact that you can, you can just shut it down or save the snapshot somewhere, and then once the user, you can just bring that back. So preemptive, you have the ability to do preemptive shutdown of the machines and then rebooting them and stuff like that. So
Yeah, we can also suspend it. So like, say we had some contention in the cloud and there's a bunch of VMs sitting there doing nothing, we could suspend them and then allow the other jobs to run and then turn them back on once those jobs are completed. So it's extremely flexible from a management perspective. Just the fact that you can actually move the instances between the physical hardware provides an easy way to do, scheduled maintenance, patching of the hypervisors, firmware updates, hardware replacements, etc.
Hi, Ryan.
I think we had a question at University of Alberta. Go ahead.
Yes, can you hear me? Ryan?
We can, yeah.
Good. Actually, I have a few questions. First one is about the management layer. Do we have such management functions like reservation of VMs? Like we book, schedule some VMs ahead. The second question is about the SDN, the network layer. Do we? Because I saw you currently you support about 50 nodes. How about the performance so far? Do you will you use like dedicate SDN provider later? The third question is about the storage layer. Sorry, maybe too many questions. Let me finish it at first, okay? The storage layer. I'm just wondering, can it support the live migration with Ceph very well? In the I don't know, in a formal storage space. Yeah, that's about it.
So the first question I believe was, do we provide scheduling within OpenStack itself? So currently we do not provide any scheduling within OpenStack. It's a first come first serve. There's a project of excuse me, I think it's INFN. It's the Italian lab, and they've developed a scheduler for Havana, and we're currently running Icehouse. So there's actual patches to the code to get this to work, but it essentially provides some sort of a fair share scheduler within OpenStack. So it gives you the ability to actually queue up VMs if you don't actually have the resources available. So this is something that we're definitely interested in. We haven't had time to fully explore it yet, and so we'll be looking into it. So basically at this time, if there's no physical CPUs available for you to run, you'll get an error message, no valid host found. The second question about VXLAN scaling. So we actually have 104 nodes. We are working at UVic. We have a project called the ONC, Ocean Networks Canada. They have actually 64 physical machines that they've made part of this cloud, and it's going to be given to people that are doing sort of ocean-related research, and they'll have access to these resources. So that's an additional, with hyperthreading, it's an additional 2,048 cores. And we've done a bunch of network testing using iPerf, and we're essentially able to get 9 gigabits per second between VMs on different hypervisors. As for future directions with the networking overlay, we're quite interested in the Juno switches, and they provide the Open Contrail to do all the networking, and the performance on that I've heard is excellent. At this time, we don't have any Juno switches available to us, but potential future upgrades might include a new core switch for the cloud, and then exploring that possibility.
So this Juno switch is still the software-defined network, right?
Yeah.
Okay.
And the final question about Ceph. So the ephemeral images actually run on local hard drives within the hypervisors. So the persistent volumes that are running directly from Ceph migrate, instantaneously because there's no data to be copied except for the memory. Whereas with the ephemeral ones where they're running from local storage, we can actually do live block migration between 2 independent servers So basically, it copies over the contents of the image, syncs up the memory, and then shuts it down on one and brings it up on the other. So there's essentially no noticeable difference except for there's a lag between when the VM is started to be migrated and when it ends up on the new hypervisor.
So no data migration?
The data migration happens through libvirt and KVM. So there's some flags you have to actually set within the OpenStack configuration to allow live block migration.
Okay, thanks.
Okay. I have a question. So for the Windows people, they like to have a little bit better graphic support. Do you have any plan to include the Spice protocol in it?
So our console is the Spice console, if that's what you mean.
The client side, right? The client going to connect via the Spice protocol client.
Yeah, I'm not 100% sure if you can get direct access at the from a Spice client to the VM once it's booted. I'd have to look into it, but essentially, if you just enable RDP on your Windows VM, then I feel the performance there is probably going to be a better experience than using a Spice console, but I may be wrong.
Yes, you are.
Okay, because with the Spice console, at least with the built-in one, the cursor mapping and stuff is off, and so I have my cursor down there and I have my actual cursor up top, and so if I try to go somewhere, it goes off the screen. But that just made me a limitation of this Java client.
We tested the Spice protocol, and I have to tell you, we should look into that because it's outperformance many other things.
Okay, yeah, I'll definitely look into it.
Yeah, the second question is, what is your backend storage? Are you using Ceph or the Swift, the one come with us, OpenStack?
So we use Ceph for everything. So we provide the Swift API through what's called the Rados gateway. So Ceph provides the Swift API through the Rados gateway. So the block storage is directly from Ceph, and then the object storage is through the Swift API.
Last question. Do you have any document for this that you can share with us? Because I want to move our KVM cloud to this OpenStack, and we kind of need some help.
Documentation on deploying OpenStack?
For like you set up this stack right here.
We do have documentation. So what we decided with OpenStack, there's several different options for deploying OpenStack. So you could use an automated deployer like Fuel, which is provided by Mirantis, which basically is sort of a point and click, and it deploys your cluster. It's quite slick. I've used it to deploy a virtual cluster, and within an hour or two, you've got an OpenStack cloud up and running. So what we decided was we wanted very intimate knowledge of every single component within OpenStack so that we could troubleshoot it properly. So we actually deployed it using XCAT, which is what we use for deploying our current HPC clusters, and a bunch of bash scripts. And then the documentation, we wrote internal wiki documentation on design decisions and different things like that. So we can definitely collaborate, and I could probably give you copies. It's just that a lot of the content is going to be in bash scripts and stuff like that. So.
Oh yeah, we that's what we do. We use bash script for all our deployment stuff like that, including the live migration in the KVM stuff. So yeah, great that you can share with us. Thanks.
Yep.
I believe we had another question at UFC. I see our time's running short. If any site has to leave, feel free, but we can continue taking questions for a couple more minutes. UFC?
Do you have any performance benchmark on commonly used scientific softwares on virtual environment? That's exactly my question.
It was a little bit quiet. Can we?
Yeah, we can't hear. If there is someone speaking, we can't hear it.
Commonly used scientific software. Have you done that?
The only benchmarking we did was when we were deciding between using to enable hyperthreading or not. We were running the HepSpec benchmark that's used sort of for benchmarking Atlas jobs.
What kind of benchmark is interested in? kind of benchmarking? Like?
Yeah, so I don't know what kind of benchmarking you're interested in. The main reason for our initial benchmarking was to see what the performance was between hyper-threaded and non-hyper-threaded hypervisor nodes. And what we found out was that although an individual job may run a little bit slower, the overall throughput was higher. And it gave us a lot more flexibility because now instead of only having 640 virtual CPUs, we had 1,280. If you have specific software that you're interested in, then we could probably work with Belade and we can do some testing. I know Belade was kind of interested in doing sort of a LinPack type test just to see what kind of performance we get.
All right. If we don't have any other questions, or do we have any other questions? Speak up. And if not, I'd like to thank you all for attending and thank Ryan for his great presentation today. Stay tuned as we have more seminars coming up in the future. So thanks again, everyone.